Okay, let's have a look at how to find a basis for the kernel and range of a transformation matrix. So by the end of this video, you'll be able to know what the kernel of a transformation matrix, how to find the kernel of a transformation matrix, how to find the basis of a kernel of a transformation matrix, what the range of a transformation matrix is, and you'll be able to do it twice apparently, and then how to use the rank nullity theorem to your advantage. So what is the kernel? The kernel is everything in the domain which maps to the zero vector under the linear transformation. This is the official definition. So let's do an example of how to find the kernel. So what is the kernel of this linear transformation? All you need to do is equate every single coordinate to 0 and then solve. This may involve Gauss-Jordan elimination, it may not. In this case, we just did a little matrix, and then the solution space of equating all the coordinates to 0 is your kernel. That's it. So how do we find the basis for a kernel? Alright, here's another matrix, transformation matrix, and we want to find the kernel. So we can tell here that x plus y equals 0 and y plus z must equal to 0, and these are the coordinates that we're dealing with, and those are the defining conditions. So rearranging all of these terms, this is the kernel. That's it. That's all the kernel is. And then finding a basis, we just take out the y, and then the remaining coefficients that we're left with is the basis for a kernel. Let's do that one. Let's do another example. So let's try find a kernel for this, and then you can find the basis. So this one you do need to perform Gauss-Jordan elimination, and once you do, you find that your x, y, and z equal to 0, which means that the kernel consists of the 0 vector and has basis, and also just the 0 vector and has dimension 0. So the empty set, that's what that is. Let's do another example. So let's try to find the kernel of this one. You perform Gauss-Jordan elimination. As you can see, you have a missing variable there, or you have a free variable. So you just do what you usually do when you're finding a solution space, and define it, and then you get your basis for the kernel. And this has dimension 1. And essentially, as you can see here, that all maps of y will map to 0. There's just no y in the transformation of this. There's no y in the transformation function. This one is just another example of how to find a basis for a kernel. I haven't walked you through this one, but it's just here if you want to do an extra example, just to make sure that you've gotten the hang of it. And this one as well, just to make sure you get the hang of it, do as many examples as possible, and here's all the working out. So now that you know what a kernel is and how to find the basis of one, let's move on to range. So essentially the range is all of the numbers in your domain that you put into the function and what you get out. It may not necessarily be the entire codomain. So the range is a set of vectors in our codomain which are used when the vectors in our domain undergo the specified linear transformation. Let's do an example. So here is our transformation function, and this is our range. That's supposed to be a 3 because there's 3 vectors there. And so the range is just the span of the basis vectors of our domain. So you put all of that through the linear transformation. This is the functions we get, and since they're all linearly independent, we don't need to check for redundancies. You can see there's a 0 there, there's a 0 there, so completely, that's the range, that's it. You just put the standard basis vectors through whatever vector space you're in, and that's it. So the rank nullity theorem, revisited. Recall how the rank plus the nullity equals the number of columns. Rank is the dimension of the column space and the row space, they're equal. The nullity of a matrix is how many basis vectors a null space has. And the null space is actually the kernel. So hopefully you can see where this is going. The dimension of the range plus the dimension of the kernel is also equal to the number of columns. And it is given by this formula. And you may think, okay, that's nice. It is very nice. So let's do an example. Alright, so let's try to find the kernel of this. We found that it was the empty set, and it has dimension 0. So if we just learnt that the dimension of the kernel plus the dimension of the range equals the number of columns. So if the dimension of the kernel is 0, that means our range is going to have 3 basis vectors, which is very handy because you don't need to do any Gauss-Jordan elimination, you don't need to check if it's redundant, you just know that these vectors are linearly independent. Those are all the 3 vectors that you use for your range. And that's it. So essentially you learned how to do all of this. So well done, and yes, I'll see you in the next video. Good job.